Welcome. In this video, we're going to talk about the kids and the chocolate bar problem. So this problem is one of my favorites. When you hear it, it doesn't look like it has very much to do with graph theory at all, but it really has a beautiful application of graph theory that has to do with trees as a really nice solution to this problem. So what does this problem say? It asks, what are the possible values larger than 9 such that many children can equally share 9 chocolate bars? And then we have a restriction with these 9 chocolate bars that we're sharing with more than 9 children. We can't cut each bar into more than 2 pieces. So you can picture you're hosting an event and kids are coming along to this event, and as a reward you want to dish out some chocolate, and you have 9 chocolate bars to dish out that reward. But there's more than 9 kids coming, and you want to make sure that there's an equal sharing of the 9 identical chocolate bars. If one kid gets a whole chocolate bar and the other gets a little tiny scrap of a chocolate bar, it's going to be a disaster. We can't have that. So they need to equally share these pieces of chocolate. So our job is to think of all the possible ways that this problem could be solved, all the possible ways that the chocolate can be equally shared, and to make sure that we don't cut each bar into more than 2 pieces. So give this a try. Think about making pieces of chocolate and sharing them in an equal manner, and write down your solution in the first step. Just guess at as many possibilities for n as you can. Okay, so hopefully you're able to come up with 1 or maybe even 2 or possibly more guesses at the ways that this could work. One of them that maybe is the natural one to think of is you have 9 chocolate bars, and each chocolate bar is cut in half. So we'll draw a little red line showing that they've been cut in half, and this would successfully serve 18 kids. So one possible solution looks like that with n equal to 18. Let's try to think of one more before we move along. All right, so one other possibility could be cutting each bar at the 1/10, 9/10 point. So if we chop it right there so that there is 9/10 on the left and 1/10 on the right hand side in each of the scenarios, then you could serve 10 kids, because 9 of the kids could get the 9/10 chunk, and then one kid could get 9 1/10 chunks. So there's 2 possibilities down on our page. Our job is to find all of the possibilities. So there might be some more out there. We're going to use some graph theory to help us out. Now, before we flip to the next step in our problem, this is step 1, I would like to write down this number c. So c in the problem is saying that it represents the equal amount of chocolate. So c in the first part was equal to 1/2. Every kid got a half of a chocolate bar, and we were able to serve 18 of them. If we're only serving 10 kids, then the capital C value could be 9/10. Let's try to build a graph out of what we're talking about. Okay, so step 2, we take the examples from step 1 and we build a graph out of it. So the kids are going to represent vertices, and when they're sharing a chocolate bar, they're going to have an edge between them. So the first example that we came up with above had n equal to 18. So what would that look like as a graph? So we have a kid as a vertex, and that kid is sharing with another kid, and the chocolate bar is represented by that edge that's between the two kids. And there's a cut that allowed us to share a 1/2 and 1/2 amount. Now, the graph itself doesn't have the cut. The graph just has the edges and the vertices, but for the purpose of this diagram, I wrote in the red notation just to visualize what's actually happening beyond the graph a little bit. So we repeated that picture 8 more times. So the other example that we came up with had n equal to 10. And this time we took our 9 chocolate bars and we shared them in a different way. We had one kid that shared with one other kid, and there was a 1/10 and 9/10 cut made. Remember, we're only allowed to make that one cut, and we did this cut 9 times so that the chocolate was equally shared. So the graph would end up looking like this, where we have, this little cut where the kid in the middle here is getting that equal amount of chocolate shared 9 times. Okay, let's take a look at the next step. So in this graph, for some reason, we're not supposed to have any cycles. It's impossible to make a cycle. Let's think about a cycle and then see if we can decipher what some problem with that cycle might be. So if we have a vertex representing a kid and then another vertex, and let's say our cycle is of size 3. On this cycle, there is 3 chocolate bars. So the total amount of chocolate is 3, and the total amount of kids that are there is also 3. So each kid would get an average of 1 chocolate bar. Depending on how we cut up the chocolate bars, it might be 1/2 and 1/2, and then it might be like 1/4 and 3/4, and then maybe we don't want to give this last one too much. It might be like 1/3 and 2/3. But every kid is supposed to get an equal amount of chocolate. Now there could be other vertices here which could sort out the equal amount of chocolate. This is not just the only part of the graph, the cycle. The cycle could be connected to other things as well. But if we kind of zero in on one part here, let's say we take a look at this part right here. We have this child getting 1/2 plus 2/3 of chocolate. That is too much chocolate because there's 9 chocolate bars in total and there's more than 9 kids. So that means that in order to equally share, each child has to get less than a bar. So that's the reason why we need to now put this into words for why we can't have any cycles. So on a cycle, at least one kid gets too much chocolate. And let's say that we have a cycle of size L. And on that cycle of size L, at least one kid will get a chocolate bar or more of chocolate. Since on the cycle, we're equally distributing L chocolate bars, and every kid cannot be less than 1, else it doesn't distribute all the way up to L. So this is a problem because the initial problem states that every kid is supposed to get less than a whole chocolate bar. So this completes the proof of why there's no cycles. If we want to remind ourselves how much does each kid get, just to clear this up a little bit, let's remember that there is n kids to begin with and 9 chocolate bars. So those 9 chocolate bars are equally distributed to n kids. This gave us a capital C value that we talked about earlier in step 1. So n itself is something larger than 9. That's what the original problem said. So C is 9 divided by a number that's larger than 9, so you will always get this equal amount of chocolate being shared as some value less than 1. This is where we have a problem with the cycle because someone on the cycle is getting 1 or more. Let's move on to step 4. So this graph that we're building, the kids in the chocolate bar problem, turns out to always be a tree or a forest. Let's think about why this might be. In an earlier video, we talked about how there was a relationship between cycles and trees. In the previous step, we just discovered that there are no cycles in our graph. Let's try to remember some of the other properties of a tree. So, first of all, a tree has exactly one path between every pair of vertices. That's the definition. And then furthermore, we learned that a tree has no cycles, it's connected, and the tree formula is true. And then furthermore, we learned that if any 2 of those 3 properties that we just listed is true, then the graph that we're talking about is a tree. So we know that it has no cycles. If we went one step further and said, okay, well, what about if it's also connected? That would be 2 out of 3. That's where our proof can start. So we'll have 2 cases. We don't know that it's connected or disconnected. So case 1, we'll say our graph that we're trying to discover things about is connected. And then the second case, the only other case that we could possibly have, in case 2, we will discuss what if our graph is not connected. So starting with case 1, if G is connected, and we also know that our graph has no cycles from the previous step, that's 2 out of 3. So we can take these 2 facts, fact 1 and fact 2, and combine it using the 2 out of 3 property to tell us that G is in fact a tree. Okay, in the other case, G is not connected. Here, let's look at each connected component. So each connected component, by case 1, we've talked about a connected graph. Each connected component is indeed a connected graph, and the whole graph has no cycles, so we discovered that each connected component is also a tree. And that's exactly what makes a forest. So therefore, G is a forest. So either we get G as a tree, or we get G as a forest. And if we return to the very first step, we came up with 2 examples, and then in the second step, we represented those examples as a graph. If we look back, we did indeed get a tree and a forest. The first example here was a tree on each connected component, so that makes up a forest. It's not a very interesting tree, but 2 vertices that are connected does indeed make a tree. In the other example here, we had a legitimate tree. It's all on one connected component, and it meets the criteria of being a tree. Exactly one path between all the vertices. Or you could say, it's connected and there's no cycles, so we immediately know that it's a tree. So our question is still, are there any other possibilities? The grand finale of our problem comes in step 5, where we find all the possible choices for n. And we're going to take the 2 possibilities from the previous step and make cases out of those and go further into each one of those cases. So in case 1, our graph is a tree. So n is what we're trying to discover, and n is equal to capital V, the number of vertices, and in any tree, the tree formula is always true. So V is equal to capital E plus 1. Capital E represents the number of chocolate bars in our problem, which is 9. So we have 9 plus 1, which is 10. So lo and behold, that is the example that we came up with, where we have a tree as n equal to 10. Every other possibility that you come up with as a tree, it must have 10 as the result. And anything else that we come up with must be a forest. So any other n value would be case 2, where we're looking at a forest. So let's move on to that. Okay, so the first thing that we're going to do is introduce some variables. We're going to individually look at each of the trees within the forest. So E sub I and V sub I will represent the edges and the vertices that are on a particular tree within our forest. And then capital T will represent the number of trees in total that make up this forest. So how about to kind of play with these new variables, let's just jump back to our picture from before and write down what we're talking about. So in the n equal to 18 case that we have at the top of our screen right now, if we're to look at each one of those variables that we just talked about, so there was a V sub I, there was an E sub I, and then a capital T. So what would each one of these be in this particular case? So V sub I represents on the ith tree, there are 2 vertices. On the ith tree, there is 1 edge, and if we count up all of the trees in total, so tree 1, tree 2, all the way up, there are 9 trees in total. Okay, let's return to where we were in the problem. So next, all the chocolate is equally shared. That was one of the very first conditions of our problem. So if we take a look at each tree, the chocolate is equally shared on those trees as well, because every kid gets the same amount of chocolate. So we could look at the number of edges on a particular tree and say we'll divide that up by the number of vertices on that tree, and we would get the equal amount of chocolate that everyone gets. And this would happen on all the choices of the trees. So if we made up another variable, let's say j, let's say we're looking at the jth tree, we'll look at the number of edges and the number of vertices on that jth tree, we would also get that equal amount of chocolate. So if we take a look at this equation, how about we get rid of the denominators? We'll multiply the denominators out, so multiply both sides by v sub j, and we would get v sub j multiplied by e sub I, and that would equal e sub j multiplied by v sub I. Now let's remember, these are trees, so there's a relationship between the vertices and the edges. There's always one more vertex than the number of edges. So v sub j is the same as e sub j plus 1. all multiplied by e sub I, carrying from above. And then e sub j would be multiplied by the tree formula, e sub I plus 1. So looking at both sides of this equation, we have an e sub I multiplied by e sub j on both sides of the equation. So we end up with e sub I multiplied by 1 on the left and e sub j multiplied by 1 on the right. So what that says is that every single tree in our graph has the same number of edges. It doesn't really matter whether you're looking at the first tree or the second tree or the fifth tree, all of them have the same number of edges. Because there's a relationship between the number of edges and the number of vertices on a tree, we can also say that all the v sub i's and v sub j's are the same. So we can write down, for all I and j. And we kind of already discovered that if we look back at the tree that we came up with from the first part of our problem, we noticed that. We said, oh, okay, yeah, every single tree in our graph has one edge and two vertices. What we just proved is that you have to get that result. If there's a tree with 4 edges, then the next tree also has to have 4 edges, and so on and so on. And this similar idea with the vertices, it has to be the same on each of our trees. Okay, so let's return back to our problem below. Okay, so now that we know that every single tree has the same number of edges and the same number of vertices, let's try to come up with all the possible values of n. So we know that the number of edges is 9. And we know that our graph is a forest right now in case 2, so it's been split up amongst a number of trees. So 9 has been divided up among these particular trees. And each of those trees has e sub I edges on it. So the number 9 is an integer. The capital T is something bigger than 1. So there's only so many possibilities for this. Capital T could be 3, and we could have 3 times 3, giving us 9. Or capital T could be 9, and we could have 1 edge on each of the trees. So from here, let's take a look at the possible values for the vertices. So n is equal to capital V, the total number of vertices on our graph, and that is the same as the number of trees in our graph multiplied by the number of vertices on each tree. And if we want to look at another way to write v sub I, each of those individual parts of my forest here are trees, so we can use the tree formula to say that that's e sub I plus 1. And we've discovered that from above, the capital T value is either 3 or it's 9. When it's 3, the e sub I is also 3. And the other possibility, the or side of things, we could have capital T being 9 and the e sub I being 1. So we get 1 plus 1 inside of the brackets. So our ground result is that we either have 3 times 4, which is 12, or 9 times 2, which is 18. So there are 3 possibilities. Our problem, when analyzed in this way, has restricted us to only these 3 possibilities. It can only be 12, 18, or 10. earlier on when we were just guessing and trying to come up with values, we did come up with the 10 and the 18. We didn't come up with the 12. Now we know that that's the only other possibility. We can invite 10 kids, we can invite 18 kids, but we could also invite 12 kids. Let's return back to the start of our video and we'll discuss what that other possibility looks like. Okay, so we also have the possibility of n equal to 12. So to help us write down what this tree looks like, let's write down our v sub I, our e sub I, and capital T. So capital T, as we discovered below earlier along, was 3 different trees. For e sub I, there were 3 edges on each of those trees, and there's always one more vertex on each of the trees than the number of edges. So that gives us a helping hand. We're drawing out a graph that has 3 edges and 4 vertices, and we're making a tree out of that. And there is 3 such trees. So in this case, we would be making cuts at the 1/4, 3/4 point. So all of those cuts, we would cut up each chocolate bar, and each kid would get 3/4 of a chocolate bar. This is actually not the only tree that we could draw. We do have to abide by these rules of 4 vertices and 3 edges per tree. But if you wanted to, you could also have drawn a tree that looks like just a straight line of vertices. Then just your cuts would be a little bit different. And once again, the cuts aren't part of the graph, but you could cut it like the 3/4 point, and then the 1/2 point, and then again the 3/4 point. And every kid would still get 3/4 of a chocolate bar. So that doesn't really matter as much. Let's just wrap up this video by doing a final picture of what the chocolate bars would look like. So there's our 2 examples that we came up with above. Let's write down the third one, which completes all the possibilities. So in the final case, we cut each chocolate bar at the 3/4 / 1/4 cut point. So chopped it up into quarters, and then most of the kids are getting a 3/4 chunk all in one, and then 3 of the kids are getting 3 1/4 chunks. So that gave us a total of 12 kids to serve, and each of them are getting 3/4 of a chocolate bar, equally shared. And those are all the possibilities. So we did indeed solve the problem, took some graph theory to get us there. Thanks so much for listening to the video. We'll see you on the next one.